I'm focusing on the HuberRegressor in Sklearn, specifically its epsilon parameter. It's all about how this parameter affects the model's behavior when dealing with outliers. It's key to understanding how the Huber loss function works. I'm asking you to identify which statements about the epsilon parameter are true. This is a test of your knowledge about the HuberRegressor. This is the core question. We need to carefully examine each statement concerning epsilon within the HuberRegressor and determine whether it's true or false based on our understanding of the Huber loss function. This statement describes how a small epsilon affects the model's resistance to outliers. I will analyze this in detail with the Huber loss function. Here we are examining the relationship between a large epsilon and how closely the Huber loss function resembles the squared error loss. This statement claims there's a single, universally optimal value for epsilon. I will assess if this is always true or not based on the context of using the Huber loss. This statement presents a relationship between epsilon and the model's sensitivity to outliers. I'll determine whether this description of epsilon s impact is accurate. These are the 4 choices given in the multiple-choice quiz question. This is just the title of a possible diagram that might visually explain the effects of different epsilon values. It's not directly relevant to my explanation of lines 1 to 10. The HuberRegressor is a regression model from the Sklearn library that uses the Huber loss function, which is designed to be robust to outliers. The epsilon parameter is crucial because it controls how robust this model is to outliers. We're going to explore how changes to the epsilon parameter affect the HuberRegressor's behavior. I'll present several statements, and you'll decide which ones are true. This is the core question. We need to carefully consider each statement and relate it back to how the epsilon parameter affects the Huber loss function. This is true. A small epsilon makes the Huber loss function behave more like the absolute error loss, which is less sensitive to outliers. Think of it this way, we're giving less weight to large errors. This is also true. A large epsilon means that the Huber loss function will behave more like the squared error loss for a larger range of errors. Squared error loss is heavily influenced by outliers since large errors are severely penalized. This is false. The best epsilon value depends on your specific data. 1.5 is a common default, but it's not always the best choice. You might need to experiment to find what works best. This statement is false. A smaller epsilon actually makes the model more robust, less sensitive to outliers. These are the possible answers to the multiple-choice question. We need to carefully evaluate each option based on our understanding of the Huber loss function and the role of the epsilon parameter. I see the Huber loss function defined here. It's a clever way to combine the best of 2 worlds, the squared error loss and the absolute error loss. The equation shows that if the error is small, less than epsilon, I use the squared error, which penalizes large errors heavily. But if the error is big, I use the absolute error, which is less sensitive to extreme values. This is what makes it robust to outliers. It's like a superhero of loss functions. Epsilon is the key to understanding how the Huber loss function works. It's the magic number that decides when to switch from the squared error to the absolute error. I'll explain. A small epsilon means I switch to absolute error easily, making the model robust to outliers. A large epsilon means I will stick with the squared error for a larger range of errors, making it less robust but possibly fitting better to a dataset without many outliers. With a small epsilon, even small errors are handled with absolute error. The outcome is that the effect of outliers is minimized. Think of it like wearing a safety helmet. A small epsilon gives you increased protection from extreme shocks. When epsilon is large, the Huber loss becomes more like the standard squared error loss. The result is that larger errors are penalized more, making the loss function less robust to outliers. This is like not wearing a helmet. The model feels the impact of extreme shocks more strongly. This quiz focuses on understanding the epsilon parameter within Sklearn's HuberRegressor, a regression model designed to handle outliers effectively. I'll be testing your knowledge of how this parameter influences the model's behavior. Get ready. Let's assess your understanding of the epsilon parameter in Sklearn's HuberRegressor. Are you ready to answer the multiple choice question? I'm presenting a multiple choice question about the epsilon parameter in the HuberRegressor. Think carefully about each statement. The answer choices will test whether you have understood the impact of epsilon on the Huber loss function. We'll be looking for the correct interpretation of how different epsilon values affect the model's robustness. After you have analyzed the question, choose the options A and B because they correctly describe the effect of the epsilon parameter. I'm excited to see how well you grasp the material. I'll provide a detailed explanation of the correct answers, guiding you through the concepts and showing you why the chosen options are correct. Let's solidify that understanding. I will guide you through the quiz step by step. First presenting the question, then allowing you to select your answers, and finally displaying the results with a comprehensive explanation. It's a simple and straightforward process. I'm presenting the question to you. Take your time to read it and consider your options carefully. Select your answers based on your understanding of the epsilon parameter. Don't worry if you get it wrong. The explanation will help you learn. I will display whether your answer is correct. This will provide immediate feedback. Finally, I'll provide a thorough explanation of the correct and incorrect answers. This is crucial to cement your understanding of the HuberRegressor and the epsilon parameter. This quiz focuses on understanding how the epsilon parameter affects the HuberRegressor. In Sklearn, a popular machine learning library, the HuberRegressor uses a loss function that's robust to outliers, and epsilon controls how robust it is. Let's examine each statement about the epsilon parameter. We'll need to understand how it influences the behavior of the Huber loss function. I agree. A larger epsilon means the Huber loss will mostly use the squared error part of its formula. The absolute error part will only kick in for significantly large errors. Think of it like this. A larger epsilon makes the Huber loss more forgiving to errors, hence more similar to the squared error loss, which is very sensitive to outliers. Absolutely. A smaller epsilon means the Huber loss will use the absolute error part of its formula more often. This makes it less sensitive to large errors. The errors caused by outliers. This behavior makes the model more robust to outliers. I disagree. Although 1.5 is a common default value, the best epsilon value depends on your specific data. You'll often use techniques like cross-validation to find the epsilon that works best for your situation. I disagree again. A smaller epsilon makes the model more robust to outliers. It's less sensitive to the influence of extreme data points, making it more robust and less affected by outlier errors. Epsilon is a Greek letter used here to represent the parameter that controls how sensitive the HuberRegressor is to outliers. It's the key to understanding how the Huber loss function works. I'll break down how epsilon influences the model's behavior. A smaller epsilon makes the Huber loss function more like absolute error loss, which is great for handling outliers. It's less forgiving of large errors. A larger epsilon moves the function closer to squared error, which is more sensitive to outliers. Think of it like this. A smaller epsilon is like having a stricter referee calling fouls more often. A larger epsilon lets the players get away with a bit more. This is part of the Huber loss function formula. If the absolute value of the error is larger than epsilon, we use this equation. It prioritizes the magnitude of the error. I find it helpful to think of it like this. The model cares most about how far off a prediction is. The bigger the miss, the larger the penalty. Let's not forget that epsilon represents epsilon. A smaller epsilon makes the model less affected by outliers. It acts like a shield against influential data points that could skew the results. Imagine a smaller epsilon as making your model more resistant to those outliers. A larger epsilon makes the model more susceptible to outliers. It's like removing that protective layer that I mentioned before. The outliers have more influence on the results. Think of a larger epsilon as letting those outliers sway the model more easily. This is the title of the quiz, focusing on the epsilon parameter within the Sklearn's HuberRegressor. I'm testing your understanding of this important parameter. Let's dive in. This question asks you to identify the correct statements about how the epsilon parameter affects the HuberRegressor. Remember, HuberRegressor uses the Huber loss function, a clever compromise between the squared error loss and absolute error loss. I'm asking you if this statement is true. Think about the Huber loss function. It's a blend. If epsilon is large, the squared part of the loss dominates. This statement is therefore true. I'm checking whether you understand the impact of a smaller epsilon on the Huber loss. A smaller epsilon value means that we'll use the absolute error portion more often for large errors, which is why the model becomes more robust. This is definitely true. I want to see if you recognize this common misconception. While 1.5 is a frequently used default, the ideal epsilon depends entirely on your data. You need to find the best value through techniques like cross-validation. So, this statement is false. This statement tests your understanding of how epsilon relates to outlier sensitivity. A smaller epsilon makes the model more robust, meaning less sensitive to outliers. Therefore, the statement is false.